Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be doing some topical questions for paper 1 on the topic of superposition for Cambridge A-level physics. And as always, these questions come from the Papa Cambridge set of topical past paper questions, specifically for the paper 1 questions. And I'll leave a link to the questions in the description, and you can use these questions to prepare for the topic of superposition, which it's commonly thought of to be one of the harder, if not the hardest topics in AS physics, in the first year of A-level physics. It is quite tricky, and I think the concepts can be quite difficult, but hopefully some of these questions will help settle some of those uncertainties. And today we're going to be looking at questions 880 through 891, and these are going to be based on stationary waves. Now, the first question is 880. It's from the March 2020 exam. It's question paper 1, variant 2, and it's question 26 from that paper. We're told that a musical instrument is made by using a long tube with a mouthpiece at one end, and the other end is open and flared as shown. The musician maintains stationary sound waves with a node at the mouthpiece and an antinode at the other end. And the lowest frequency of sound that the instrument can produce is 92 Hz. And we want to know what the other frequencies that can be produced by the instrument are. So we have 92 is obviously the first, and we want to know what the second and third and fourth modes of vibration, or the fundamental frequency and then the overtones. Well, I'm going to just model this instrument as a pipe that is closed at one end. So something that we're kind of familiar with already. So if I model this instrument as an open pipe that's open at one end, then I can sort of try and figure out what's happening. And so let's look at the first mode of vibration. Let's start with the 92 Hertz. So what does that look like? Let me just label this first mode of vibration. The first mode of vibration is going to be one in which I have the simplest vibration, meaning there's going to be a node at the closed end. Remember, your mouth goes over the mouthpiece, closes that end. If that end is closed, it cannot vibrate. It must be a node. There'll be one node and one antinode. So the node opens up into an antinode, which is at the opening or the open end of the instrument, the flared end in our case. I'm just ignoring the flare because it's not really going to change any of the physics of our setup. And then I'm going to draw a dotted line to show how the standing wave would change if it were shifted by 180 degrees. So the sound wave is up and then down and so on. And I'll just label this end a node, that's N, and the length of this mouthpiece we'll call L. And so that's not going to change. And what we can see is that there's a quarter of a wavelength fitting inside L, fitting inside the instrument. And so the length is a quarter of a wavelength, lambda over 4, which means that the wavelength is 4 times L, which we don't know the length of this tube. Now, if I use the equation that the speed of sound, I'm going to call it C, is equal to actually sound, so we'll just call it V, so we don't confuse ourselves with electromagnetic waves. But V is equal to F lambda, that's the wave equation. That means that this first frequency, the fundamental frequency, which we'll just call F1, is V over lambda, and that's V over 4L. And V over 4L is 92 Hertz. Okay, so we don't really have a definitive answer, but we have a description of the first mode of vibration. Now, the second mode of vibration, obviously we can't choose A, B, C, or D because obviously 92 Hertz is for all of them the first frequency, it's given. What about the second mode of vibration? The first overtone, if you like, the second frequency that's possible. And again, it must be a node. So always start with your closed ends being nodes, your fixed points being nodes, and your open ends being antinodes. And then see what's the next simplest picture that I can draw. Well, I had one node before, so I need two nodes now. And so I'm going to go up, come back down through a node, and then I'm going to be open an antinode rather, at the open end. And then at some later point in time, I'm going to have the dashed line. So this is my second mode of vibration. I now have two nodes, and I also have two antinodes. And in this case, I'll just move this down a bit. And in this case, let's describe what's happening here. The length of the instrument is not changing, but the wavelength is changing. So how do we relate the two? The length of this instrument, L, now contains 3/4 of a wavelength. 3/4. It goes half a wavelength, and then the last half of half, which is 3/4 of an entire wavelength, which means that lambda is equal to 4L over 3. And this frequency F2 is V over lambda, which is 3V over 4L. Well, 3V over 4L is 3 times what we had in the first case, so it's 3 times F1. 3 times 92 is 276 Hertz. So we actually are getting somewhere. Now for the second mode of vibration, I realized that I can eliminate A and B because only C and D have 92 and then 276. Remember, again, you don't need all this working. If you remember what the frequencies are, what the first 3 frequencies are for a pipe that's closed at one end, then by all means, you can just sort of write the answers down. But this is how you would go about calculating it. And so I have the first mode and the second mode, but unfortunately, I am stuck between C and D, so I have to draw one more diagram to figure out what the third mode of vibration will be. And so the third mode of vibration is going to be one where I have 3 nodes. So I'm going to have a node and another node and another node, but I must have an antinode at the end. And so node at the closed end, 2 more nodes, and then an antinode at the open end. And then the dashed line is the complement to the solid line. And so here I have 1 node and 2 nodes and 3 nodes. That's the third simplest frequency, the third mode of vibration of the standing wave. And the length here, now we have 1 complete wavelength and then 1/4 of another wavelength. So 1 1/4 is 5 over 4 lambda. And this means that the wavelength lambda is 4/5 of the entire length of the tube. And so the third frequency, the second overtone if you will be 5V over 4L. But look at that, that's 5 times the fundamental frequency. That's 5 times 92. And this would be 460 Hertz. So the third one must be 460 Hertz, which means now we can definitively choose option C as our answer. Again, you wouldn't need to do all of these workings. If you remember the relationship for the frequencies for a pipe that is closed at one end, you'll realize that it's V over 4L and then 3V over 4L and then 5V over 4L. So it's odd multiples of V over 4L. And then you can just take odd multiples of 92. 92, 1 times 92, 3 times 92, 5 times 92, and then 7 times 92, which would give you 644. But from first principles, this is how you would calculate it. You didn't need all the calculations that I did, but if you were stuck, just remember what your pictures look like. You always have nodes at the fixed points, at the closed ends of a pipe that is closed at one end, and then an antinode at the open end where the sound wave can have the greatest amplitude. An antinode is the points of greatest amplitude. That was quite a long question, but quite a common type of question that you will see in superposition. Question 881 is from the summer 2020 exam. That's May-June 2020. It's question paper 1, variant 1, and question 27 from the paper. We are shown a diagram with a string that is stretched between fixed points x and y. There's a stationary wave on the string. And the solid curve is showing the string at a position of maximum displacement. The dash curve shows the other position of maximum displacement. The straight central dash line shows the mean position of the string. And point S on the string is directly above point P. Point T on the string is directly below Q. We're given 4 statements and we want to say which one is the correct one. So if I were to redraw this diagram, actually I wouldn't need to redraw this diagram, but what I can see is that point R firstly does not move. Remember, nodes don't move, so that point of the string rather doesn't vibrate. Okay, so there's no vibration. R is a node. So a short time later, point R will be displaced. That is not true because R doesn't move, right? But what about the next statement that says points S and T on the string move in opposite directions? Well, at one point in time, S is at the highest point and T is at the lowest point. So what this means is when S starts to move down, then obviously the whole stationary wave is going to move, and T at the same instant time is going to start moving up. And that's going to happen always in the opposite direction. So when T reaches the maximum point above Q, S is going to be at the minimum point below P. And they'll always be moving in the opposite direction. So when S now moves up, then point T moves down. And so actually what we can see immediately is that this is correct. We don't even have to read the next two statements because that is correct. Always good to read the next two statements though to make sure that you haven't missed something. C says the distance between P and Q is one wavelength. They can't trick us. We know that's not true. P and Q are half a wavelength apart. So that's not true. And lastly, D says 2 points in the string that are equal distances from R vibrate in phase. Also, that's not true. If I took a point here, we have P, Q, R, S, T. Let's call this point V maybe. And V is equidistant from R as Q is, then these 2 points would be out of phase. When one is moving up, the other one's moving down, and vice versa. So they'll be 180 degrees out of phase or completely out of phase. So the correct statement is option B. Points S and T move in opposite directions. So we didn't need significant amount of calculation there. The next question is 882. It comes from the summer 2020 exam, question paper 1, variant 2, and it's question 24 from the paper. Now we are shown a diagram where there's an experiment producing a stationary wave in an air column, and a tuning fork placed above the column vibrates and produces the sound wave. The length of the air column can be varied by altering the volume of water in the tube. Open the tap, the water level changes, and the standing wave changes. The tube is filled and then water is allowed to run out of it. The first two stationary waves occur when the air column lengths are 0.14 and 0.42 meters. We want to know the wavelength of the sound wave. Now, a little note about this question is you actually don't need both the lengths given. It might have been there to sort of throw you off, but you definitely don't need both of them. So here's my tube. And at the first position, before I've even let some water out of the tube, the standing wave has the length of the air column is 0.14 meters. And I want to find the wavelength of the sound wave. So what I basically need to do is, let me just draw what this first sound wave would look like. It would have a node at the water's edge where the air can't vibrate, and an antinode at the open edge of the tube. And so like we saw in a previous question, it's going to look something like that. That's the simplest standing wave that can be formed, the first standing wave. And this distance, we'll call it L. This L, maybe L1 for 0.14 meters. Now, what we can see is that L1 is a quarter of a wavelength. So we've only gone the quarter way. We've gone from central point to crest, which is a quarter of a wavelength. So that's lambda over 4. But wait a minute. This means that the wavelength of the wave lambda is 4 times the length of this air column. We know this distance. So that's 4 times 0.14 meters, which means that the value of the wavelength, which is going to be constant, is 0.56 meters. It's the same sound wave even when we change the water level, but the wavelength is going to be 0.56 meters. So I really don't need I really don't need to do the second calculation, because if I did the second calculation, then yes, I would have a different picture. And the picture would change, but the relationship between L and lambda would still give me lambda equal to 0.56 meters. So the wavelength of the sound wave is option D, 0.56 meters. If I redid this calculation with the new column of air of length of 0.42 meters, I would still get the same wavelength. So you could save time, and without having to try and set up a system of simultaneous equations, you could have done it in with just one piece of information. So that's question 882. The next question is 883. It is from the summer 2020 exam. It's question paper 1, variant 2, and it's question 27 from the paper. The question says that two progressive waves meet at a point. Which condition must be met for superposition of the waves to occur? Okay, short, sweet. The waves must be coherent, the waves must be of the same type, the waves must be moving in opposite directions, the waves must meet in phase. I can have two electromagnetic waves, or I can have two sound waves or two water waves. They can meet, they don't need to be coherent, they don't need to be traveling in opposite directions, they can be moving in the same direction, and they don't need to be in phase at all when they meet. And superposition will occur. One will add to the other. What is important, though, like you'll know from the definition, is that for two progressive waves to meet at a point, waves must be of the same type. So if you want superposition to occur, you can't superpose a water wave with an electromagnetic wave. What would that look like anyway? You can't superpose a sound wave to a microwave. Okay, so for superposition, waves must be of the same type. If you look at this, you can kind of see that that one stood out anyway. And so even if you didn't know the definition, you could have sort of played with the logic a bit to figure out that the correct answer here was option B. Waves must be of the same type. The next question is 884. It is from the summer 2020 exam. It's question paper 1, variant 3, and it's question 27 from the paper. We're told that a vertical tube is partially filled with water. A sound wave moves down the tube and is reflected by the surface of the water. The frequency of the sound wave is gradually increased from 0 until a much louder sound is heard. Water is then removed from the tube until a second louder sound is heard. Which diagram shows the new pattern of the stationary wave that is formed? So there's a sound wave, and then there's another sound wave, and we want to know which pattern will be the second of the sound wave that is heard. So let's draw what the first pattern would look like. When the maximum sound is heard, then we have a standing wave. When we have a standing wave, then we have a node at the closed end, or at the fixed end, and then an antinode at the open end. And so the first pattern, let's assume the bottom is the column of water. So the first pattern would be the simplest one, like we always have. Antinode at open end, and then node at closed end, and then I'll draw the dotted line in the opposite direction. And this is the first frequency, we'll call it F1, and we have one node. Now what we actually want is the second pattern. So you see that's not one of the options in the choices, because we want the second pattern. The next lowest frequency that's going to give us a standing wave, basically, as I adjust the water level. Actually, I'm adjusting the frequency of the sound in this case. I'm leaving the water levels constant. And so I have the same cylinder of water, and I'm going to have two nodes instead of one. I'm going to have another node at the fixed end, and then a node somewhere in between, and then an antinode at the open end. So I'm going to have node to antinode to node back to antinode. And then I'm going to do the same in the opposite direction for the wave at a later point in time. So this second pattern, F2, has two nodes. And immediately I can see that this corresponds to option C. That's the second pattern that's going to form. And we can do this for the third and fourth and fifth patterns and so on. But also, if you look at this problem, you didn't have to do the working that I did, because we know that for a standing wave, where one end is closed and the other end is open, the open end must be an antinode. Can't be A. B, and the fixed end must be a node. So B couldn't be correct because the fixed end is an antinode. D also couldn't be correct, but the fixed end is also an antinode. So the only diagram that is correct for any standing wave is C. None of the other scenarios are representative of a standing wave. So the only correct answer was C. So you actually, if you spent a little bit of time quickly looking through the options, you could have immediately chosen option C. So just be wary in the case where I sometimes look at a question and I go through the solution before even looking at the options. But sometimes you can eliminate options immediately without having to do like really complex calculations. The next question is 885. It's from the March 2019 exam, and it's from question paper 1, variant 2, and it's question 27 from that paper. We're told that P and Q are fixed points at the end of a string. Transverse wave of constant maximum amplitude is formed on the string. P, R, and Q are the only points on the string where nodes are formed. S and T are 2 points on the string at a distance of x from R. And we want to know the relationship between points S and T. Do they have the same amplitude and are they in phase, or do they have different amplitudes and are they in phase? Do they have the same amplitude and a phase difference of 180 degrees? Or do they have different amplitudes and a phase difference of 180 degrees? Well, let's draw the transverse wave, shall we? This is point P, and in between P and Q we have a point R, and we'll label R after we draw the actual transverse wave, and then equidistant from R on the other side we have Q, and what this graph would look like would be a node going to an antinode, then a node again through R, antinode, and then node again at Q. And at a later time, we have the dashed line. Again, my drawing would not be as good as yours would be in pencil, but again, you don't need to draw if you don't feel like it. And so at a distance from R to the left, a distance x, a horizontal distance x, I have point S. If I move a horizontal distance x from point R to the right, I have point T. So they're equidistant horizontally from R. And what this means is that they are basically mirror images of one another. So whatever S is doing, T is doing the direct opposite. And since they are mirror images, we can see that from symmetry, S and T have the same amplitude. They are the same horizontal distance from R, but they're also the same vertical distance from R. They have the same amplitude because we're going the same distance on either side. Because of symmetry, that's what the sine curve will give us. But because they are doing the opposite things at the same time, meaning if S is moving down, T is moving up, they will always be out of phase, irrespective of the distance x. As long as the points are equidistant from the node on either side, they will be out of phase. They'll be doing exactly the opposite. So when S is moving down, T is moving up, and vice versa. And so these 2 points have the same amplitude, but they're out of phase, or they have a phase difference of 180 degrees. And so this corresponds with option C. And that again comes from your definition of what a standing wave is, or what a stationary wave is. Question 886 we'll ignore because it has a little bit of alternating currents, which we don't do in AS physics anymore. We covered that in A-level physics, so we'll ignore the question 886 and we'll go to question 887, which comes from the summer 2019 exam, question paper 1, variant 3, and it's question 26 from that paper. Now here we are told that an elastic string is attached to an oscillator at one end and then clamped at the other end, so the string is horizontal and in tension. The oscillator is made to oscillate vertically, and the frequency of oscillation is gradually increased from 0 until a stationary wave is set up in the string. The frequency is then increased further to frequency f. when a second stationary wave is set up in the string. And then the frequency is increased further, and we want to know at which frequency a third stationary wave will occur. So we have the fundamental frequency, which we don't give a symbol for. Then we have the second frequency, which we call f, but we want to know what the value of the third frequency will be in terms of f. So let's assume that we have this string, and we're going to give this string a length. We're going to call the length L, and it's fixed at both ends. It just has an oscillator which allows for the vibrations to happen. And the most simple mode of vibration is this one. Node at both fixed ends and antinode in the middle. Can't get any simpler than that. Okay. And for this first wave, we have this length being half a wavelength. We can see that this is only one crest. If I had another crest, I would have a full wavelength. This is half a wavelength, which means that the wavelength, lambda, is twice the length of the string, 2L. And the frequency would be V over 2L. What will the second wave look like? I still have two nodes. The length of the string has not changed, but the shape of the wave will look different. I have to include an extra node in the middle. So up goes my wave, down it comes to the node, goes to the antinode, and comes back to a node at the end. This is the second frequency, the first overtone, the second harmonic, and I have three nodes. Don't really need to label the nodes, but just so you know, we went from 2 to 3 nodes. And here the length of the string is still L, but I have one complete wavelength. So the length of the string is one wavelength lambda, which means that lambda, well, I don't need to do that either. Lambda is equal to L, and the frequency is speed over wavelength V over lambda. That's V over L, but we already told that this is F. So we can see I'm going V over 2L, V over L. The next one is obviously going to be 3 over 2 V over L, or 3V over 2L. So we can immediately sort of say that it's going to be 1.5 F, but let's prove it. The next picture is going to have one extra node, so I'm going to have 4 nodes. So I'm going to have 1 node, and 2 nodes, and 3 nodes, and 4 nodes covering the same length. And my graph is going to go through all of these points with 4 nodes. And as always, I draw the dashed line to represent 180-degree phase shift. That's what my standing wave will look like. And so now I have node, and node, and node, and node. And here the length of the string is still L, but this equals, well, one wavelength and another half of a wavelength. So it's 3 lambda over 2, 1.5 wavelengths, which means that the wavelength is 2/3 of the length of the string. Now the frequency, as we've calculated before, is V over lambda, which in this case will be 3V over 2L. But wait a minute, V over 2L was, or V over L rather, was F. So this is 3 over 2 times F, which is 1.5, 1.5 F. And so the third stationary wave occurs when the frequency is 1.5 F. That's option B. So a little bit of a tricky question, but if you understand the rules of standing waves, you probably wouldn't even have to do this calculation as I've done it. However, when solving these problems, I like to go back to the basics from the ground up so that you understand where this particular solution comes from. Now the next question is 888. It is from the winter 2019 exam. That's October-November 2019. It's question paper 1, variant 1, and it's question 23 from that paper. Now we are told that a source F emits microwaves with constant amplitude. The microwaves hit a metal screen P and are reflected. A stationary wave is formed between S and P. The wavelength of the microwaves is much smaller than the distance between S and P. A detector Q is moved at a slow, constant speed from S to P. We want to know what happens to the amplitude of the signal detected by Q. And so what is happening here, let me just draw a diagram, is I have point S, which is the source, point P, and basically a stationary wave of microwaves is formed in here. And they have very small wavelength as compared to the distance between them. So there are many, many waves, but I'll just draw a few. So let's assume we have a few waves. It doesn't really matter how many, just trying to get the diagram correct. But there'll be a node at S and node at P. And it doesn't really matter if we have a node or an antinode at S, but this is what the standing wave would look like. And so we have these microwaves creating a standing wave because they're reflecting between S and P. And then we move the detector Q from S to P at constant speed very slowly. And we want to know what happens to the amplitude as Q moves from left to right. Well, we can see the amplitude. The amplitude is great there, but not so great there. But then if I move further, it's great there again. And at the node, the amplitude is 0. So the amplitude is increasing and decreasing regularly. And so I can see that and I can write it down. The amplitude increases, it goes higher, but it also decreases, and it does so regularly, does so with a constant frequency, just like a sine function will. And so this corresponds with option B. And so basically what the detector is picking up are the nodes which have 0 amplitude, and then the antinodes which have maximum amplitude, and then everything in between. But it's a constant change because it's a standing wave. And so that corresponds to option B. The next question is 889. It comes from the winter 2019 exam. It's question paper 1, variant 1, and question 26 from the paper. We have two wave pulses traveling toward each other on a long rope. The pulses have the same amplitude and wavelength and are traveling at a speed of 0.5 meters per second. The diagram shows the rope at time t is equal to 0, and we want to know which diagram shows the rope at a time of 3 seconds. Okay, so these two waves are of the same type. They are wave pulses on a string, on a rope rather. They're actually identical waves. They're just moving in opposite directions. They have the same speed even. And what I want to know is what they would look like 3 seconds after this has happened. So what I want to do is position these waves 3 seconds later and then do the superposition of them. So what distance will these waves cover? Well, distance is speed times time. They're traveling a speed of 0.5 meters per second for a time of 3 seconds. And so each wave is going to progress in the direction of motion by 1.5 meters. So wave 1 is going to move, so the left-hand side wave is going to move 1.5 meters to the right, and the right-hand side wave is going to move 1.5 meters to the left. So let's look at what wave 1 would look like 1.5 meters later. So it's going to be starting at 5.5 meters, because the starting point was 4. 4 plus 1.5 is 5.5. And it's going to end, whereas it previously ended at 5, it's now going to add at 5 plus 1.5, which is 6.5. So I have one wave, and then I have two waves, and the end point is 6.5. So for these two waves, a total distance of 1 meter is covered, and that still holds. So nothing has happened to the individual wave just yet. What about wave 2? Well, wave 2 is moving to the left by 1.5 meters. And so the left-hand side point at 7 will now become 5.5. And the right-hand side point, which initially was at 8, will now be at 6.5. But hey, this wave is identical, and it looks eerily similar to the wave I've drawn before. And so at this point, these two waves are in phase, and they're at the same point at that moment in time. So they will undergo superposition, and when they undergo superposition, they will have constructive interference. And so if I were to again draw this graph, what I would find is I'd have larger maximum amplitudes. So at the same position, 5.5 and 6.5, if this amplitude here was A, and that amplitude was A, the amplitude of the superposed graph would be 2A. And there's only one graph that actually corresponds to this, and that's option C. So again, you didn't have to write down a calculation. You could have basically done this in your head, but writing things down, if it works for you and it helps, then by all means. So interesting question on how waves undergo interference when they undergo superposition. The next question is 890. It comes from the winter 2019 exam. It's question paper 1, variant 2, and it's question 25 from that paper. We're told that a transmitter of electromagnetic waves is placed 45 centimeters from a reflective surface. The emitted waves have a frequency of 1 gigahertz, and a stationary wave is produced with a node at the transmitter and a node at the surface. We want to know how many antinodes are in the space between the transmitter and surface. Okay, so interesting question. Let's first work out the wavelength of this wave, because I want to know how many wavelengths are fitting into this 45 centimeters, because then I'll know how many nodes are there. Now, wavelength is the speed of the wave divided by the frequency. This is an electromagnetic wave, so the speed is 3 times 10 to the power 8 meters per second, divided by the frequency, which is 1 gigahertz, or 1 times 10 to the power 9 hertz. So what I get is a wavelength of 0.3 meters, which is 30 centimeters. So now that I have the wavelength, let me draw a picture, a depiction of what this would look like. So here's my speaker, and here's my reflective surface, and I have 45 centimeters, a distance of 45 centimeters from my speaker to the reflective surface. But my wavelength is 30 centimeters. So I actually have 1.5 waves in the space from speaker to reflective surface, but I have a node at the speaker and a node at the surface. So I'm going to have one complete wave, and then I'm going to have half a wave. And then I'm going to move the reflective surface closer because I didn't draw that very well at all. And so I have a node at the speaker and a node at the reflective surface, like the condition was stipulated. And so I have node there, node there, node there, and node there. But what I'm really interested in are the antinodes. So the antinodes are the positions of maximum displacement. And remember, I want this wavelength. That was the wavelength, 30 centimeters. And so I have one antinode there, another antinode there, another antinode there. Maximum displacement, where we have crests and troughs for a standing wave, that is. And so I have 3 antinodes in this picture. So when you have a question like this, find the wavelength first and compare the wavelength to the length of the distance, rather, that the wave is spread over, that standing wave. And then you can find how many antinodes and nodes there are by drawing a simple diagram or by just doing it mathematically. So that corresponds with option C. There's 3 antinodes in the space between the transmitter and the surface. Now, the last question we're going to do in today's video is 891. It's from winter 2019 exam. It's question paper 1, variant 3, and it's question 26 from that paper. In an experiment to demonstrate a stationary wave, 2 microwave transmitters emitting waves of wavelength 4 centimeters are set facing each other as shown. A detector is then moved along a straight line between the transmitters. It detects positions of maximum and minimum signal and is a distance d from the left-hand transmitter. We have to assume that both transmitters are at antinodes of the stationary wave, and we want to know which row gives a value of d for a maximum and for a minimum. So a stationary wave is set up between transmitters, and we basically want to know at which point, if we measured distance d from the left transmitter, at which point we're going to have a maximum and which point we're going to have a minimum. Now they tell us a very important fact that at both transmitters we have antinodes. So I actually can draw what my stationary wave is going to look like. So let's assume I don't really know how many waves there are, but I start with an antinode, and let's move this point again a little further. We have more waves here. And let's assume that the right-hand transmitter, I have another antinode. Okay, and then I draw the wave that has been completely phase shifted. So what do I actually have here? So this point at the transmitter is d is equal to 0. And the wavelength of the wave is 4 centimeters. So if I go from here where I've placed the x to there where I've placed the next x, that's half a wavelength, right? So that's d is equal to 2 centimeters. And if I go from d is equal to 0 to the next crest, then I have d is equal to 4 centimeters because that's one wavelength. And then obviously that's d is equal to 6. So what I can see is there's a pattern for all the antinodes. It's 2 centimeters separating each successive antinode. And obviously these points in between are going to be odd multiples of distance. D is equal to 1 centimeter, D is between 2 and 4 is 3 centimeters, and the next node is going to be 5 centimeters. That means there's a maximum at every even multiple of distance, and every odd multiple of distance has a node. So for the maxima, which are the antinodes, the position of maximum displacement, we have d equal to 2n, where n is just some positive integer value, 0, 1, 2, and so on. And this is all even numbers. And there's a minima or a minimum that the detector picks up a minimum at a node, and all of these nodes happen when d is equal to 2n plus 1, where again is n is equal to any 0 and any positive integer value, 0, 1, 2, 3, etc. And so if I want a maximum, it must be an even number, and a minimum must be an odd number. And the only row in the table where this happens is option C, where maximum is at an even number, but minimum is at an odd number. And so you can see how drawing the diagram kind of helped us there. And so the maximum happens at all even values of D, and the minima happen at all odd values of D. And so the only correct option there could be option C. And that's 48 centimeters for the maximum, 47 for the minimum. And so that was the last question that we'll do in this video. But as you can see, the idea of superposition and the concepts will be sort of thoroughly tested, and you have to understand how standing waves are formed, how standing waves work, what nodes and antinodes mean, how to sketch a graph, or how to sketch what a standing wave would look like if you have a closed pipe, if you have a stationary wave on a string that's attached at both ends, and so on. You need to know where these are. Once you have those positions of your nodes and antinodes, and you can relate the length of your string or the length of your tube to the wavelength of the wave. And usually that solves most problems in some way or the other, or helps you solve most problems. So I hope this video was useful. I hope these questions helped clear up some misconceptions about superposition. If you found this video helpful, please leave a like or a comment. Subscribe to the channel if you haven't already. From me, Mr. K, that's all for now. I'll see you again next time on Everything is Relative.